Hello again. So I'm just going to be going over one more example on datum overlap. And instead of flatness, this one is going to be covering how it applies to two mating perpendicular surfaces in an assembly. Here's the assembly. Part 1 and part 2 are stacked on top of each other, and then a pin is passed through the two parts. So in this example, I've done something similar to the last example, which is using extremely large tolerance on the overlapping feature, just to illustrate visually what's happening. The assembly, datum feature A and datum feature M are going to be in contact. Then part 2 is going to slide backwards till datum feature B and datum feature N are in contact. And then the pin is going to have to pass through these 20mm holes. If the components were manufactured perfectly with the holes at their MMC size, this is what the assembly would look like. Let's do a cross section. And the pin would pass straight on through. But of course, this is not what the assembly is going to look like in real life. There's going to be form error, there's going to be orientation error, there will be positional error. And in this example, I've only modeled the orientation error in this back surface. So this is what the as manufactured part looks like. We've got a whole bunch of orientation error back here. And when we put it on the gauge to check the part, so the red part is the gauge, the pin passes straight through, no problem. Same thing with part 2. A ton of orientation error in this back surface, the datum end surface. But once again, when we put the part on the gauge, the pin passes through just fine. But here's where it gets interesting. Despite both parts passing their inspections individually, when they're assembled together, the datums overlap, and therefore the pin does not pass through the holes. I think the obvious first question most people have is, well, how much is it overlapping? What is this number over here? And the math is easy on this, kind of similar to the last example I went over. It is the same as the overlap over here. And well, what is the overlap over here? Well, the real overlap is going to be based on the actual measured part, but the potential overlap is the lesser of the orientation tolerances J and K. Kind of similar to the previous example. So if J is larger than K, then the largest potential overlap is K, and vice versa. And finally, here's a couple graphics illustrating what an uneven overlap would look like, or a non-equally distributed overlap would look like. So in this case, the allowable perpendicularity on this top part is larger than the bottom part, and then vice versa for this. And you can see how there's, on this one, a gap at the top, and this one, a gap at the bottom. So when you are designing components and assemblies, how do you account for this? Well, the main tool you have is changing the virtual condition of the mating parts. What do I mean by this? Well, in our example, we've got a hole that is 20mm and a datum overlap of up to 5mm, which means that a 15mm pin can sneak through between these parts. So as the designer, you can do a few things with this information. The first easiest thing would be just take the pin and say, well, I'm just going to make it 15mm as the sort of largest size it can be. The other option, which is a little bit more complicated, is to increase the size of both of the holes evenly. And how do we do that? Well, we know this is the equation that got us this size. Well, let's just turn it into some variables. So x minus 5 is equal to 20 is what we want. If we're not going to do this, if we want to leave this pin as a diameter of 20. So we'll say x minus 5 is equal to 20. Well, x is equal to 20 plus 5 is equal to 25. So that's if you want to increase the sizes of both holes evenly. The third option is to make one of the holes the same size as it currently is and increase the size of the second hole. So in that case, what you would do is you would just say, well, we have to increase one hole or both holes by 5 millimeters if we want to get this 20 millimeter gap or a 20 millimeter pin to be able to fit through the holes. Well, that just means we need to make one of the holes. If we're only changing one of the holes, it needs to be twice that size. So 20 plus 2 times 5 is equal to 30 millimeter hole. And if you're looking at the size of these holes while you're designing these parts and going, well, I don't want to increase them that much. I don't want to increase the size of my holes 5 or 10 millimeters. The final option is to make the potential overlap smaller. And in this case, with such an exaggerated potential overlap, I think that would be the first step. So when I was editing, I realized that I should clarify one thing. I said that we could make the virtual condition of the holes bigger by increasing the size. The other option would be, in another case, to shrink the positional tolerance. But in this case, I've got a positional tolerance of 0 to mmc. But if we had something like 21 millimeters plus 1, 0, a positional tolerance of 1 at mmc to mn. The other option would have been to shrink this positional tolerance. Hopefully this example was helpful. Have a good one.